So in this video we're going to go through an example involving multiple reactions and illustrate how we use various extents for each reaction to solve a reaction system and inlets and outlets for a reactor. So this is just an example taken from the book, and what we have here are two reactions taking place. We have this top one here, C2H6 breaking down into C2H4 and hydrogen. And then we have C2H6 reacting with hydrogen, H2, to form two CH4 or two methane molecules. And we have this reactor here where we have some inlet, some feed coming into the reactor and some outlet coming out of the reactor. So given in the problem statement is that we have 100 moles coming in into our reactor, and then we're giving some mole fractions. We know that the mole fraction of C2H6 is 0.85, and the balance is 0.15 of inerts. And we don't know what the inerts are. They could be argon, they could be nitrogen. It's just some species that's not participating in the reaction. So it's a mixture, again, of C2H6 and the inerts. Leaving the reactor, we have all sorts of potential species. We have C2H6 if this reaction doesn't go to completion. We have C2H4, which is a product of the first reaction, H2, a product of the first reaction, CH4, product of the second reaction, and we also have some inerts that may have gone through a reactor and not reacting. We're given some information about conversion. We're told that the fractional conversion of C2H6 is 0.501, and the fractional yield of C2H6 is 0.471. And these 2 points here will help us solve for these quantities here, and we'll go through this example to show you how we do that. So first thing we want to do is write out our equations involving extent, so we know how to calculate what's going out of our reactor, all these various N species, the N1 through N5. We want to have reactions for doing that. So this right here is the equation using extents. The amount of a molecule leaving out of the reactor is equal to the amount in plus the stoichiometric coefficient for reaction 1 multiplied by extent 1 plus the stoichiometric coefficient for the second reaction multiplied by extent 2. And that's the general equation that we're going to use for setting up the species, all the different various species in terms of extent. So let's look at the individual ones for N1 through N5. So what I've done here is just written out N1 in terms of the inlets amounts and also in terms of extent 1 and extent 2. So N1 is the flow rate out of the reactor for C2H6, and that's equal to 85 moles, which is just 100 times 0.85. That's the amount of C2H6 coming in, minus extent 1, because C2H6 is a reactant, minus extent 2, because again it's a reactant for the second reaction, and 2, which is the amount of C2H4, is just extent 1, because it's only being produced right here in reaction 1, and 3 is the amount of H2 leaving. And I should point out for N2 and 3 and 4, there's no of those species in the inlet, so we don't have to worry about this part in, just like we had to do for N1. But N3 is actually produced by reaction 1 but consumed by reaction 2, so it's extent 1 minus extent 2. And 4, which is the amount of CH4 produced by reaction 2, is 2 times extent 2. And again, the 2 comes from the stoichiometric coefficient right there. And then N5 is the inerts, and that's not participating in the reaction, so it's constant, and that's 0.15 times 100, or 15 moles. And so these are the equations that we need to use to find out N1, N2, N3, and 4. And what we really need to do is find out what extent 1 and extent 2 are. And if we know extent 1 and extent 2, we can find out what all N1 through N4 are. Now, at this point, we need to take advantage of this information that's given. The fractional conversion is given, and the fractional yield is given. So these are the equations that we're going to use here. Fractional conversion is equal to the moles reacted in the reactor divided by the moles fed. The fractional of unconversion, or the fractional of unconverted, material is 1 minus F, and it's equal to the number of moles unreacted over moles fed. Or in other words, this is equal to the number of moles leaving the reactor, the number of moles unreacted that are leaving the reactor as unreacted species, divided by the moles fed, and that's equal to 1 minus 0.501, and then F is the fractional conversion. So we can go ahead and just rewrite this as the number of moles unreacted, that's equal to, again, as I said, N1 over the number of moles fed. In this case, that's 85 moles, and that's equal to 1 minus 0.501. So we now have a reaction, or we have an equation that relates N1, which is the outlet of C2H6, or N1 is the amount unreacted, the amount of C2H6 that enters the reactor and leaves as unreacted, as it relates to the fractional conversion, and the amount fed, or the inlet. And so if we take this equation here, along with this equation right up here, so if I just take this equation, plug it into that equation right there, I'm going to get myself a new rearranged equation in terms of extent 1 and extent 2, and in that case I will have the equation 42.4 moles is equal to 85 moles minus extent 1 minus extent 2. And this equation, let me just put in a box in that. So that's one equation that we get from the fractional conversion that relates extent 1 and extent 2. Now we need one more equation to be able to solve for extent 1 and extent 2, and we'll get that, if you haven't guessed, from the fractional yield. But this is the, as I said, this is the equation here. We need this one right here in order to, along with the other equation, to solve for extent 1 and extent 2. And again, to remind you, this was derived from the fractional conversion. Again, we went from here all the way to here. So let's look at how we can use our fractional yield to give us an equation that relates extent. So in this case, here's our two reactions again. Fractional yield is defined as the moles of our desired product. In this case, C2H4 is our desired product. This is the species that we want, C2H4, divided by the maximum moles possible. And again, to remind you, the maximum moles possible assumes two things. It assumes that all of the C2H6 converts over to C2H4, or in other words, 100% conversion. It also assumes that this reaction doesn't take place. So we ignore this reaction right here. And we also, as I just said, assume that all of our C2H6 is converted to C2H4. So to do that, to determine the maximum moles possible of C2H4, we need to go ahead and we can use our the amount of moles of C2H6 coming out. So let me just write max moles C2H4, and that's equal to 85 moles C2H6. So that's how much we start, and we assume that all of this right here, the C2H6, converts over to C2H4, and if that's the case, then it's 1 mole C2H4 over 1 mole C2H6. And where did I get that? I just got that from the stoichiometric ratio from the equation here. 1 mole of C2H4 is produced per mole of C2H6, and that means that the maximum number of moles of C2H4 is 85 mole. And that's great. So now we know that part. And the moles of desired product, that's the one that's actually formed. And if you recall from the equations we wrote, that's actually moles desired product. That is equal to N2, which is equal to extent 1. So we have the moles of desired product right down here. We have the maximum moles possible right down here. So now we just need to use this equation to help us come up with something that will help us solve for the extents. So let me just shrink this down here. Give me a little more room to write. Okay, At this point, we just need to use the fractional yield equation. So the fractional yield was given in the problem statement. 0.471 is equal to N2 over 85 moles. It's equals to extent 1 over 85 moles. And again, to remind you, 0.471 given in the problem statement, that's this fractional yield here. The number of moles of our desired product, or what comes out of our reactor, that's N2, and that's also extent 1, based off the extent equation. The number of maximum moles, well, we just determined that up here, and we found that it's 85 moles. You see here 85 moles there, 85 moles there. So we have this fractional yield equation, and this gives us a key bit of information, because now we can go ahead and solve for extent 1. So we have 0.471, 85 here. We can just take 85, multiply it by 0.471, bring this up over here to get our extent 1, and the extent 1 turns out to be 40 moles. I'm going to put a box around that. So this is great. I have extent 1, but I previously solved for an equation for extent 1 and extent 2 from the fractional conversion. And let's go ahead and do that. Let's go ahead and use the fractional conversion that we previously derived along with this extent 1 we just derived to go ahead and find out what extent 2 is. So these are the two equations we have. This was taken from the fractional yield. We used the fractional yield to derive extent 1. This is the equation that we got from the fractional conversion, which is in terms of extent 1 and extent 2. So now I can just go ahead and take this equation, plug it into here for extent 1 to solve for extent 2. And I do that, I get extent 2 is equal to 2.6 mole. Let me put a little box around these two. So those are the key piece of data we need to go about solving this problem. And now we know extent 1 and now we know extent 2. We can plug them into the equations that we started out with to find out what N1, N2, N3, N4, and N5 are. So here we are back to the original setup of our problem again. We have all the information given, and then we had these equations that we wrote out for the different species based off the extent, again, inlet plus the stoichiometric coefficients multiplied by the extent, and we derived these at the very beginning of this video. Well, now we know what extent 1 is and extent 2 is, so we just need to take these values, plug them back into these equations up here to find out what N1 through N5 are. So if we do that, and it's just simple algebra at this point, we get the following answers. Just like I've shown you right here. These are what we get for N1 through N5, the various species. And then again, N1 is moles of C2H6, N2 is moles of C2H4, etc., etc. And that's the general procedure for solving problems involving extent and multiple reactions. We need to go ahead and set up our various equations for the different species or chemicals coming out of the reactor in terms of the extents. If there's one equation, there'll be one extent. If there's if there's one reaction, there'll be one extent. If there's two reactions, two extents. Three reactions, three extents, etc. And you just have to set up these equations as appropriately and then use the information that's given to you in the problem statement, whether it be fractional conversion, fractional yield, selectivity, or whatnot, to find out what the extents are, and then plug these back into the original equations to get all of the different species coming out of our reactor. And there you have it.